the class, our first lecture on SSG. You're welcome to our first lecture on SSG227, Engineering Computer Graphics for 200 level systems engineering. So we are starting today, and I hope we are going to enjoy the course. I enjoy to teach you. I hope you enjoy to be taught and to learn. We learn from each other. I learn from my students, just like they learn from me. In this introductory class, we want to ask ourselves, why are we studying engineering graphics and solid modeling? Are we trying to train you to become graphic artists? Is there any reason why you must study this? I will leave that as an open question to start with, and I will move on. So we look at design, visualization, and product making. Design, visualization, and product making. By the time we have done 2 courses, you should have a very clear idea what an engineer means when he says he's doing a design. Then you will know how solid modeling helps you to visualize and how it leads to making things. If you are asked to name the most important subject in your engineering training, what will your answer be? I am not trying to dispute your answer. You have your own answer, I have my own answer. And I'm not even trying to say somebody is right, the other person is wrong. I will try to give my answer and prove it. So maybe when you have an opportunity, you can go to the chat room, give your own answer, and try and defeat me. And let us see who is right. Let the person who has better logic supporting himself be the right person. It is not just because I'm teaching engineering graphics. I think your most important subject may be what you are taking now. Engineering graphics or solid modeling may be your most important engineering subject. So don't take it lightly. You are going to learn a number of skills here. The skills you learn here can actually be sufficient to earn you your daily bread. It can be. So it can be important enough to be what you will live on. So I just want you to first of all bear that in mind. So it's not just one course you are just taking and then the other courses are more important. It is a very important course. Might actually be the most important course you will take. Why did I make that choice? My answer is deeply rooted in what is the purpose of engineering and why are you in a university studying it? If you can answer those questions deeply, you will begin to see why engineering graphics and solid modeling may in fact be the most important subject that you will take. But let us go on. Okay, let us ask another question. What is technology? What is technology? Technology is as old as man. No matter, as long as you are a human being, no matter what age, whether it's ice age, stone age, whatever, everybody has to have technology. For the simple fact that big and brainy as an elephant might be, big as its brain might be, you will never have a place where some elephants gather human beings to be in a cage and are feeding them to be doing their whips. It is the opposite. No matter how big an animal is, no matter how small it is human beings that domesticate other animals, not the other way around. I am claiming that the primary reason why that is possible is because human beings have technology and the other animals don't have technology. Products, services, and artifacts that enable man's domination of his environment is technology. Products that allow man to act beyond his personal endowments. You will see from the example we will give that when a man acts, he's not just depending on how endowed he is. If a man wants to move fast, he will not do it by running. He can do it by entering a car or entering an aeroplane. And when he enters a car or an aeroplane, he will be faster than a cheetah on land and he'll be faster than a bird in the air. Even though the birds and the cheetahs are naturally better endowed to move faster. What is the reason for that? Technology. There's a mango on the tree. You can see the mango on the tree here, okay? These individuals want the mango. An elephant, a giraffe, a hawk, a monkey, and a man. So see them, 1, 2, 3, 4, 5. So if these 5 individuals compete for this ripe mango, remember, an elephant is stronger than a man. A giraffe has a longer neck than a man. A hawk can fly, a man cannot fly. Even though you may be able to climb a tree, a monkey can do that better than you. And now you want to reach this mango. So who is going to win? More importantly than who will win is what will be the individual strategy to reach the mango. If you can answer that question, you are answering the question of what is technology. Our answers to this question can define technology. Think about it. You will understand why technology is as old as mankind. Every human society has technology. For example, see Mr. Elephant. See how strong he is. I'm sure you don't want to enter a quarrel with an elephant. You have no chances. He's so large and powerful with a big trunk that can pull down the mango tree if necessary. He can uproot the mango tree if he wants. So he doesn't need anybody's help to get the mango. Look at Mr. Giraffe. See, he just goes there, he extends his long neck, and he eats the mango before you try. He's already there. Maybe the birds can even beat him there because the birds can fly and quickly take the mango before he reaches it. Or a monkey can climb the tree and go and pluck the mango. Now, the question is this: to answer the question of what is technology, what do all these have in common? All this, the elephant, the giraffe, the bird, the monkey, they have natural ability, little technology. They are all using their natural ability, and that is their strategy. That is the strategy they deploy to win any battle. Their natural ability. A man, even if it is a fight for life, suppose they want to kill each other, the elephant is going to depend on how strong he is. If he can step on you, you are dead. If you can avoid him stepping on you, you may have a chance. And so on. A lion will try to eat you up, or bite you, or tear your skin. But a man will not do any of those things. A man is going to depend on technology to fight. And that technology can kill all of them with ease because it has been developed. Even the primitive man can just shoot a bow, or can just shoot an arrow with his bow and kill the animal without even being near it at all. So we are beginning to understand technology from the human angle. A man does not think about his natural ability to solve problems. He does not think only about his natural ability to solve problems. He sees a mango, he might take a long stick to bring down the mango. That's one method. That's already technology because his hands or neck may not be as long as that of giraffe, but he can get a stick that is longer than the giraffe's neck and bring down the mango. Or he can climb a tree, though he can't do it as dexterously as a monkey, but he can use a shorter stick. Or he can make a plan and tell himself, knowing that I will need a mango in 3 years, let me grow some now. Maybe 3 years time, the tree will be matured and I can start eating mango in my own compound, and nobody will even compete with me there. He plants an orchard. He can even decide to make a business out of it. And you can see when you see mango trees planted in a line or in several lines, you know that it is not occurring naturally. Somebody has done that. So technology is what moves us beyond the natural endowments and enables creativity and innovation. It is our distinguishing mark. That's what differentiates a man from the animals. That is one thing that if you don't know the difference between a human being and an animal, think about technology. That is a clear demarcation line between a man and an animal. Now let us look at another thing again. Don't forget, we are trying to answer the question, what is the most important subject you are taking in your study of engineering? Science and the scientific method. I am quoting from Wikipedia here. You can Google this and you can read this and more of it in your Wikipedia. Science and the scientific method, a method for discovering knowledge about the natural world based on falsifiable predictions which we call hypothesis. You make a prediction, which if facts show it to be false, you make another prediction. So that we call such predictions hypotheses. Testing those hypotheses experimentally or empirically, they mean the same thing. And developing peer-reviewed theories that best explain the known data. So you keep going in a cycle until you get better and better theories. And after that, you use the best theory as an explanation of what is happening in reality. When you do that, you are using the scientific method, or in short, you are doing science. So when we talk about science, this is what we mean. We do not just mean physics, chemistry, biology. It is the fact that those things you call physics, chemistry, biology is because they are based on this type of strategy. That is why they are all called sciences. So anything that depends on hypotheses, testing those hypotheses, developing theories, and going in circle until you get better theories, all that is called science. That's modern science. Whatever science discovers is kept in a database of the world's knowledge and can be used for any purpose, good or bad. The origin of the modern scientific method occurs in Europe in the 1600s. A chain of research events, involving a chain of research events from Copernicus to Newton, which resulted in the gravitational model of the solar system. First of all, they found that it's not the sun revolving around the earth, it's the earth revolving around the sun, and the solar system is being held together by gravity. And the whole universe is a gravitational field. The theory of Newtonian physics was used to express this model. And over the years, better and better theories have been found. For instance, Einsteinian gravitational theory was proved to be a better theory than Newton's own when you go to far, far longer distances. If you are on Earth, Newton may be okay, but by the time you start looking at the bending of light, bending of rays of light when you have solar events, then you can see that there are other theories that have come up. But that is how science works. Now, technology can be primitive. We have looked at science and technology. For instance, you could build a workshop for molding metals inside your hut. Much of our local craftsmanship is based on primitive technology. So you build your workshop like this, with mud house, with thatched roof, and you have a fire oven, and you can make some things. Some people are still doing this in some place in northern Yoruba land, Shaki. They are still melting. They go and take railings on the highway and go and melt them into pots and pans using the most primitive technology, and they say that is their heritage, okay? So primitive technology could be your heritage, and you can be very proud of it. But I think you are in the universities to study engineering to improve on that. Or you can build a story building with a balcony like this proud builder has done. See his house? It's a story building, and see the staircase. All you have are 3 pieces of wood, and then you just cut and tie. No need for any nails. Just use some bark of a tree to just tie them around, and your stairway is ready, and your house is ready, and this is good. So but this can be a starting point. But do we have to remain there? Do things have to remain like this? Visit Makoko, about 5 kilometers from the gate of a university that I've been standing here for 60 years, and you will see how primitive we are as a people. You are studying engineering primarily to be able to change this narrative. What skills do you need to have? What skills do you need to have so that we will not just continually iterate in this kind of primitive technology? What can we do to change that? Like, see how this is the fishing technology that you will see when you go to Makoko. Just some people in the mud pulling their boats that they carved out of some wood, and it works, but it's primitive and not hygienic. If there's a disease, COVID or cholera or anything, it will take some of them away. because they are not benefiting from modern technology. Now, we have seen that we're looking at science and technology now. We have seen that technology is not just science. It is in fact much older than science, whereas we are dating modern science to 1600. Technology is as old as man. Technology goes as long as you know any human settlement of any type, of any nature. There is some technology there. The technology may be primitive, but there is technology. When leveraged with science, technology can be modernized. We can modernize technology by leveraging it with science. That is where, so do not use the word science, technology, engineering interchangeably. They mean specific things. Go to the dictionary, go to Wikipedia, you will know what science is. Science is something specific. Technology is another thing specific. Technology are the things you use to conquer your environment. You can use instinct to get technology. Nobody needs to write any equation to get a stick, to pluck a mango tree. Yet that is technology. People have been using wheels to roll wheels on wheelbarrows to be carrying their stuff to the market for generations, long before you discovered the vibrations or strength of materials. That's technology. But they were primitive technology that have now become modernized. In the present time, technology is being vigorously mediated by science to alter the way transportation and energy systems are deployed. Electric vehicles are replacing the internal combustion engine after 150 years of dominance. Internal IC engines have dominated transportation for more than 150 years. But that is changing now. That's changing, and it is changing because of new knowledge, new science has shown that it is realistic to harness energy from the sun, to harness energy from the winds, to harness energy from the oceans, to harness energy from the tides, and so many other from biomass, so many other renewable systems are now beginning to replace the internal combustion engine. And after some time, some children will be born who will not even know how an internal combustion engine that you are used to now, how it looks. Just like many of you don't even know what we were doing 40 years ago when we were undergraduates and we were typing things with a typewriter. You don't even know what a typewriter is because technology has completely mediated the dominance of typewriters and has moved us some other distance. So renewable energy methods are replacing fossil fuels. Nigeria is still trying to create cattle colonies to make beef using Stone Age methods, even when all these things are happening. Now, you are Nigerians like me, I hope, and I hope it will be our conversation to see how we will move away from this kind of Stone Age thinking. If we cannot do it as a government, we should be able to do it for ourselves and become rich and live outside the limitations of the Stone Age system. That is something, that's the challenge that I think every one of us should take instead of the arguments. So the politicians and other people can be doing that, but as engineers, we should be able to get sufficient skills to know that we are not supposed to just be using Stone Age thinking in the technology that we're going to deploy. We can therefore define engineering. I can write this equation: engineering is technology mediated by science. The plus here is that you use the knowledge gained from science to mediate technology to give you engineering. Or you can say that when science is deployed for the purpose of creating technological products, goods, and services, we are doing engineering. Or you can say engineering is science when it is employed to create products and services. Whichever way you say it, you are saying the same thing. Engineering is actually when science is used to mediate technology directly to create better products, better services, better goods, using much more advanced knowledge. I'm sure you know that the electronic circuit that I create here cannot be learned by going to apprentice yourself with a motor mechanic at the gate. And then therefore, you will now be able to understand all the circuits, all the capacitors and the diodes and all the semiconductors and all the things here. It will take you to learn base algebra. You will need to have a lot of math to even begin to understand what's going on here. That is modern engineering. Those are the results of modern engineering. They are not something you can, they're not things you can just get by your natural instinct. So when we rely on our basic instincts to create products, and we follow no theoretical underpinnings of known scientific results, we are in primitive technology or cheap craft. We are not doing engineering. By the time you are doing engineering, you are no longer relying only on your basic instincts. The instincts will still come. You are trying to create products, but you are not just creating the products by your instincts. You are trying to create the product based on scientific knowledge, based on computations, based on engineering calculations, based on simulations, based on animations that you already know what the result will be before you build. When you are doing all of those things, you are doing engineering. If you are not, and you can still make stuff, you can create a pepper grinder, you can make a helicopter like the person who puts a fan on top of a B2 and gets a battery-operated motor to roll it, and he says he has made a helicopter. You can do that. You can do those things. Let us see how many people will fly with that. That's still primitive technology or cheap craft. So we now arrived at what engineering is. Remember, we are trying to see the role that graphics and 3D solid modeling plays in your training. I am propounding the theory that it is the most important subject you will take. And if you think it's because I am the person teaching it, think again, because this is not the only thing I teach. I teach other subjects. So I'm having at this for a reason. In engineering, you are learning to make products and services by using science to leverage technology. If you do not do that, you have not done engineering. And that is a very terrible, terrible condemnation on what we have been doing over the years. Because many times our universities, we in the universities, we limit our engineering to the science. Whereas the science is just the beginning. It's to be leveraged to create technological products. If you are not careful, even you yourself, coming this late to at this late stage, if you are not careful, you will learn only science. And you will not move into using it to leverage technology. If you are not careful, you can pass all your exams by just staying in the science. But I am challenging you to take some decisions so that you will actually use that science to leverage technology and make products. You know, let science make people reject us and decry our theory. When you talk in society and say you are from the university, theory, what they are saying is that you have not moved your science far enough to let them see products that you can make. And that is the challenge I'm giving you at this early stage in your training. Make up your mind that you are going to go beyond theory. Now, if you think that means you will not learn theory, think again. You are going to learn theory. You are even going to learn more theory than the person who is than others. But you are going to learn the theory for a purpose. You are going to learn it to have enough science to be making things like this. You are going to learn enough math to turn it to data analysis, data analytics, and so many other things that will actually yield products and services. For instance, you know that MTN or any of these things, they just give you a code if you pay them 1,000 naira. And that code already, with that code, your phone already knows how much you paid and how much to credit you. That's a product. That's a service. That's a lot of theory. It is based on the theory of combinatorics and random number generation, which you cannot, the amount of theory behind that is immense. And that's why the biggest companies today are not oil companies. They are not even manufacturing companies. If you are manufacturing a car, like all the big companies like Toyota, General Motors, they are no longer the biggest companies in the world. Companies that are doing very theoretical things like data analysis, like Facebook, Microsoft, Amazon, and all those ones, are much bigger companies than those. You can see now how much theory is underpinning to this technology. So don't just think because our people are rejecting theory, therefore you will not do theory. You will do theory, but you will do theory because if you don't, you are going to be creating primitive technology by instinct, and you will end up as a half-baked craftsman. Now, you don't want that. The solution comes by learning 3D, begins in 3D solid modeling. It just begins. It's not, doesn't end there. Because with 3D solid modeling, you can create models of reality around yourself. And I will show you how you do that in this course. Then you use scientific methods to analyze the models. Anything that exists physically must exist geometrically. We need the geometry of shapes and changes in shapes. You will be doing this for your entire stay, University of Lagos. Initially, you are just going to be looking at the geometry of shapes. Then later on, you are going to be looking at the geometry of changes in shapes, because those ones lead to strain, they lead to stresses, they lead to failure. And those are the things that will determine the amount of material you use to design your door handle, your slab, your brake pad, your engine block, your gearbox, and many other things you do. So you need to see how these things connect, and that they depend on the theory, but the 3D solid modeling is your first bridge to use that theory, that science, to leverage technology in order to create products. You can see why it is therefore exceedingly important. Even if you don't agree that it is the most important thing, at least I hope you will at least agree with me that it is very important. Okay, so solid geometry models, the skills you learn here make it possible to express your problems geometrically. The ideas you have, you can express them geometrically. You can express them in 2 dimensions, you can express them in 3 dimensions, you can express them photorealistically, and you can express them in animation, you can express them in simulation. Modern engineering graphics differs significantly from the old. You can now create realistic images, you can animate the models, you can simulate loads and failure scenarios, which leads to full design, analysis, and optimization before spending resources on physical models. So those are the things, those are the benefits of solid modeling. So we are going to teach you solid modeling from the point of view of design. We are not just going to be showing, you are not just going to say, okay, let's get an A in engineering drawing and forget it. We are going to show you the connection it has with virtually all the other courses you are going to be taking. And then you will be relying on it as you are taking all those courses, because you will still be able to make those solid models so as to use the shape changes to do your failure analysis, to do your optimization, to do your design and analysis in later courses. Engineering. Learn to use scientific theories to optimize the designs. Then you use modern manufacturing methods to make new products. We are handicapped in the university because the main machinery to be able to turn that into actual physical things are often not as available. You need things like computer numeric control machines, which we call CNC, 3D printers of different types. There are now metal printers, though they cost a lot. The latest price I got for a metal printer is about $360,000 to $370,000. So they are still beyond our ability to purchase them, but the technology is moving in that direction, and it is somebody who has 3D solid modeling background that will be able to operate those machines, because there's nothing to operate in those machines. The whole thing is to do your origination of your 3D solid models. That's why preparing you with your 3D solid modeling prepares you when opportunity comes to use such things to manufacture things, because industry is becoming miniaturized. So you can make things in small industries now, cottage industries, using much more powerful new technologies. And then you can do things with laser cutting. We already have a small CNC machine in our project. Some people may have access to that if they work with us. We have a couple of 3D printers. We will likely allow some of you in your projects to use them, but we are going to pay, because it is not We have to maintain those things. We will determine that they are not university property. So, but we will try and see how we will expose. Some of you may have enough money to buy your own. So 3D printers are becoming cheap enough for people to have their own personal ones. But we have about 6 or so in our project. The cost of the other machines continue to fall. So these are the things that I want you to know, that to use any of these things, all you need really is 3D solid modeling. You don't need to do much. You can even do your 3D solid modeling now and send your output to somebody who has CNC machine. He will give you a price and you can print it, he can manufacture it for you at a cost. How many pieces do you want? So the design, that is why we talk of product as a service. Product making now is almost becoming a service, because the turnaround time in modifying things to get better products is so short. It's not like before. So just like you have software as a service, you are now having PaaS, which is product as a service, becoming the correct way to do things in our age. Your environment. To avoid the double jeopardy of theory on the one hand and primitive technology or cheap craftsman on the other, you use solid models to model your environment. I will explain to you what I mean by that. I'll give you examples, and the examples are just examples. You will learn to do more things on your own. You look especially at engineering innovations, limitations, failures, and possible improvements. So when you see things around you, I will give you examples for you to see what I'm talking about. Look at innovations around you. Look at limitations of what is happening. Maybe you see something, but it's not doing the work it's supposed to do well enough. It's limited one way or the other. You might say, oh, can't we improve this thing? When you are thinking that way, you are thinking like an engineer. When you see failures, I will show you some failures in this lecture. When you see failures, you have to ask yourself, why is there a failure? Everybody knows there is failure, but the difference between an engineer and a non-engineer is that the engineer is endowed with ability to quantify the failure and to redo the design so as to remove the cause of failure, because he can quantitatively analyze why failure occurred. The whole thing we are teaching you, all the courses, mechanics of solids, mechanics of strength of materials, mechanics of fluids, mechanics of heat, thermodynamics, elasticity, plasticity, all the things you will be doing in later years are to give you the ability to quantitatively evaluate innovations, limitations, failures, and profile possible improvements. All of these are going to be based on the models you have made. The models you have made are the central thing that you are doing, you are using all those things on. So when you do not know how to properly make a 3D solid model, you have cheated yourself, and you are going to be limited to theory, only knowing some science, grab, pour, pass, give to the lecturer, and go about society, and everybody's laughing at you. You see, because yourself an engineer, can't do anything. So that is the thing. If you want to avoid that, then you must know that when somebody says, you can see, if I say, if you're asked what's the most important subject in your engineering training, what will your answer be? My answer is engineering graphics or solid modeling. So this is the reason why I am saying that, because every other thing we will teach you, you will need that background to be able to do all your analysis, design, improvement, failure analysis, and innovations all around they will all revolve around the models you have made. If the thing you are thinking about is something physical. If it is not physical, that's another question. Okay, so let us begin with creative design. Let me first of all ask, can everybody see my table lamp? Can you see this? Admin, is my table lamp coming up?
Yes, sir, we can see
Admin?
I can hear you, sir. I can hear you, sir.
Let me just be sure that I can hear you. Can people see my table lamp?
Yes, we can see it. We can see it, sir.
Okay, you can see. Okay, so this is my table lamp. It's on my table. So I have several of them. I have one that is yellow. I have one that is blue. Okay, so you can see this one now. It's the yellow one. It's on the table. Now, I used Fusion 360 to draw it. So you can see it's 3 dimensions. So this is a drawing, a 3-dimensional model of this lamp. So this lamp has this top here. This is where the light is. Let me just show you the light so you can see the light coming here. Okay. Okay, so this is the table lamp. Armed with 3D solid model software, your creative design training may begin with modifying objects you have successfully turned into your models. For example, on the left is the picture of my reading lamp. The top right, this one, is a 3D solid model of the same lamp done in Fusion 360. I did this in Fusion 360 after seeing this lamp. Okay, inspired by the lamp and its model, the middle and the lower right-hand side show a new lamp design using animated revolute joints of Fusion 360 component assembly. So see, this one now is my own improvement on this lamp. The improvement of this lamp, what it does is that it can, this one cannot fold. This one cannot fold, but this, my own design, can fold. So you can see how your creativity can be inspired by something you have seen. If you do 3D solid modeling, you can be playing with it. You can be playing with something and say, okay, how can this thing be different? And you get a new design. And you can analyze it. You can check, for instance, you can analyze these joints. You can do the animation and then get better animation and then get, for me. Now, suppose what you are interested in is to make this lamp so that it can be packed. If you do that, you can see this one, therefore, is superior to this. That's an example. Okay, so inspired by the lamp and its model, the middle and the right-hand side shows a new lamp design using animated revolute joints of Fusion 360 component assembly. So you will learn about revolute joints later on, creating an improved lamp that can more easily be packed and traveled with, for instance. That is one thing you might be able to do. I have a comment here. Okay, so that is something that you can take a look at. That's something you can do. Now, before I move on, I want to show you some things I will challenge you to have. As an engineering student, before you complain, University of Lagos doesn't have this, University of Lagos doesn't have that. All of you, every one of you should have a tape, personal tape. If you're an engineering student, go buy one for yourself. Go buy a tape. You can see a tape like this. Buy one. This is my own tool set. I wear my belt. When I go about campus, I will show you some of the things that I've done. I put my tools inside this. I hope you can see my toolbox here. I have inside it, I have a digital vernier caliper. It's digital, so it will give me accurate measurements. So this is a tape, a digital vernier caliper. Go get one, no matter how much it costs. Own one. Don't start saying you don't have in our lab. You get yourself one, your own. Apart from the screwdriver and so many other and some other things, get yourself a knife, not for fighting. You need to cut some things. This is a mechanical knife and some other things that I have in my bag here. I think there are some things, minimum stuff that you should have. I will show you what you do with some of these things as I move on in this class. So there's no need pretending you're an engineering student and you are just going about just cramming some mathematics formulas and you don't do anything with it. This is where, if you are going to fail as an engineer and you are going to be creating cattle colonies to rear cattle in the Stone Age, the failure starts from your 200 level. If you continue cramming like you'll be cramming all along and you do not consider that the practical courses actually have some important additional important skills to your work, you're going to get your degree. You can even get a first class and go jobless. So that is it. But if you just learn, if you are an expert in solid modeling, that is even enough to give you your daily bread. If you now add simulation to it, you are going to earn a good living anywhere you are in the world. If you add animation, simulation, and design to it, you are going to be a top dog anywhere you go in the world. Even saying there's no job in Nigeria, there's no job in Nigeria. There is nobody that can add solid modeling to some programming and simulation. It is not possible to be jobless. It is not possible. Not possible. So it doesn't matter. If you want to run to America, fine, you can go. But it is not because you cannot survive in Nigeria. If you do this, I've been training engineering students for a number of years. Let me not frighten you by telling you how many years. But what I will just tell you is that I don't know any student that can program, I can do simulation, I can do solid modeling. I don't know any that is jobless. I don't know any. In fact, they reject jobs that are paid .something million to go and earn dollars somewhere. Some of them do that without leaving Nigeria. Some of them do that by going to some greener pastures. It's their choice. It will be your choice. But I want you to know that the number of skills that are in this thing is enormous. Just the number of skills that will come out of this. So you learn those skills. When there is ASU strike, my courses will continue to go on online. So you go online, you will see it. So if you want to continue learning, then these courses are strike proof. So your future cannot wait until government and everybody else. If we are going to separate Nigeria, if it's going to take 5 years to do that separation, your future cannot wait. If you wait until that time before you study, your hunger will kill you. So you have to move on. You are young and time doesn't wait for anyone. So let us now move on to failure analysis. I'm going to show you some things about failure analysis. I will put it as a question. Before I go to failure analysis, I think I'm getting used to my voice now, and I want to give you a 15 minutes break. We will continue this course in this lecture at 10 past 3, so that you can go and relax on what I have said. And then please don't forget, the video, the audio, everything will be available online. It will be available for you to download after the lecture. So it is up to you. So even things we did not cover well, you will also have opportunity to ask me questions online through the chat room. You can also ask questions offline. If you don't use the available opportunities I've given you, you have yourself to blame. But we will continue after the break on failure analysis. Thank you. Admin, we are break now. Yes, before I go on, I want you to know that when I teach online, I expect there to be a reasonable amount of response from the students. You can go to the chat room anytime and make your comments. Usually there are 1 or 2 lecturers that are with me, and you can even ask questions which may be answered without my stopping the lecture, because somebody else may be able to answer your question. If there are things that you have difficulty with or you think we should change, please feel free to tell us. We will not get angry. Just let us know. We want to know how to improve this so that it will be better for going on from here, or for the people that will come after you. So if there's any way we can make things better, let us know. We will appreciate that. Just use the chat room, and I will be giving you some questions once in a while to use the chat room to solve. I've already told you that you should get some tools for yourself. I will now show you what you do with it. So for instance, when I showed you this, if you have this on your table, how did you think I got from here to here? I took measurements. And I found out that essentially this bottom thing is an equilateral triangle with all these curves. So that's how I did this. So I took the measurement. I looked at the angle made by this on this plane, and the angle, this one is just a curve, this one is movable. So all those things you have to measure. Sometimes you have to measure exactly, and that's why you need a digital vernier caliper. And then sometimes you have to measure some long distance. There are other equipment that I've not told you about. For example, there's one other equipment here. This is another interesting equipment you can Google on and find. I don't see why any engineering student should not have this. This is a laser. This is a laser meter. So you can measure distances, very long distances, much more than what your tape can measure, just using a laser pointer. And I don't remember how much I bought this, but it's not too expensive. And I don't see why you cannot have this yourself. So just get some of these things. These ones can measure lengths, can measure angles, can measure areas, can do that, and just gives you all that answer on the screen. Just have your own copy of this. You can do a number of things with this. Just trying to turn this thing off. Turn it off. Okay. Okay, so you get yourself ready to engage your environment. The whole idea is your environment. You will see as we go on, you see the number of things in my room, the number of things that I just draw. Just draw them, and then you can just do some little engineering analysis on them. And those things are going to give you ideas. In fact, I think in engineering, we should be training you at the beginning the way. Remember your friends in environmental design. You can see that when you came, you see them loitering around in the open spaces, drawing the environment. That is how engineering students should also be using the 3D solid modeling to be drawing all the small things, all the things you think you can make, things that have been made that are not made well, or that are made well that can inspire you. Draw them. Then you can do analysis on the 3D solid model. So if you do that, then you now use all the courses, all the theory courses we are teaching you to be able to use the eye of those theory courses to look at those things. And you will now see that engineering is to show you how to interact with your environment and be making things using science. If you use your ordinary instinct, just make the thing anyhow. That's cheap craft. The difference is that the theories we teach you should come down through your 3D solid modeling, simulation, animation, and design analysis to now get a reason, quantitative reasons why you can improve those designs. So I've just showed you one thing now, showed you my table lamp. And my table lamp, we just drew it. We didn't talk about any forces or anything. Let me take you to another challenge. Now, the question in failure analysis is this. Does it concern you? Are you concerned at all that your engineering faculty and your university is littered with failed concrete benches? Have you seen the concrete benches on campus? Or if you have not seen them, I will show you. I will show you. So don't worry. If you are closing your eyes as you walk around, I don't close my eyes as I walk around. I took my phone camera and I went around and I took some pictures that I will show you. Did you even observe them? Is there anything that you, as a student in systems or mechanical design, can do about them? Are you as helpless as everyone else? Can you take inspiration, innovation, and challenge to do something different, to see what is wrong with these things? How can they be changed? Do you offer opinions on these failures and similar issues? Do you say, oh, this is the reason why this thing failed? Do you talk, open your mouth and just make some comments like that anyhow? What are the bases of such opinions? What is your opinion based on? Is your opinion based on your instinct? Are your opinions related to any scientific and engineering computations? Is there any engineering calculation you have used to reach your conclusion? If so, you are doing failure analysis. If you can use a scientific or engineering computation to reach a judgment of why something has failed, when you do that, you are doing failure analysis. That's one of the major jobs that an engineer does, failure analysis. So as to prevent failure, we do failure analysis. If not, you are simply as ignorant as the rest of the talkers. And you know, Nigerians can talk forever, Even if you triple the cost of credit, they will still continue to talk. Nothing can stop them from opening their mouths and talking. Maybe Buhari should ban talking on the phone too, so that you stop talking. Okay, that's another thing. It's not only Twitter that should be banned. Okay, see failure. Have you seen these pictures? What I'm showing you here, have you seen them in engineering? For instance, this is in the shed in front of civil engineering department. What is it?
We can't see them yet, sir.
You can't hear me?
We can't see the slide yet.
I'm not sharing my screen.
Screen, but you are sharing your screen, but we can't see the slide. Okay, we just saw the pictures now.
I'm waiting.
We just saw the pictures now, sir.
I don't know. Please be telling me, because as soon as I see it, I just thought everybody has said it. Okay, somebody is commenting. Let me just see what. Okay, it's visible now. Okay, somebody says it's visible. Please, if I'm too fast and you are not seeing what I'm pointing at, please, just like the admin guy has stopped me, please make sure you stop me, because as I'm saying it on my own screen, I'm assuming that you are saying it. Sometimes the internet is slow these days. I don't know why. I've been struggling with slow speed, despite all the big money that I paid for my own internet. Okay, so this is a failed concrete bench, and it is in front of civil engineering, University of Lagos. Of all places, it's in the front of the department whose main trade is in concrete manufacture, and a simple bench there is in front of the place, disgracing us all there. It is there for us to see. Even this floor is failed. You see the slabs there that are opening. Those are things that should not be seen in an engineering faculty. In any engineer, where engineers are, these are things you shouldn't see. So you see, this second one is in the lagoon front. I don't know whether it's still there. The shed in front of civil engineering, this was supplied in 2005. They were brand new in 2005. They began to fail as early as 2006. I observed the failure because I was there in 2006 when they started failing. So this is what you have. If you go to the lagoon front, one thing I want you to take note of how thick this bench is. And so the person probably saw how these ones have failed, and he thought, if I make it big, if I make it very big, it will not fail. That's not engineering. That is just instinct. It was launched by the chairman of council, Dr. Gamele Onosode, in 2013. Failure started within 5 years. This thing, within 5 years of installing concrete benches, they started failing within 5 years. It was launched 2013. So by 2018, they started failing. These ones are in the DLI. These were more heavily built than the previous two. Instead of 2 legs, they have 3 legs. Yet, that did not prevent them from failing. These things were never designed from an engineering perspective. They just called some artisans. Okay, sure, you can look at this thing. Yes, yes, sir. Okay, go and make it. So as far as the artisan is concerned, this is what he thought he saw. And he thought if instead of 2 legs, he can put 3 legs, then the thing will not fail. But unfortunately, that is not how it works. It still failed. Even the legs were failing. So this is another one. 3 supports instead of 2, yet failures were more dramatic. Dead on arrival. I visited the DLI before it was commissioned. And I can tell you that some of these failures happened even before they were handed over to the university. Some of the failures. So it's what I call dead on arrival, DOA. Some were already failed structures, even before the buildings of DLI were commissioned. These chairs had already failed before commissioning. They are still there. If you have time, go to DLI. Not even to go to DLI, just look around campus and to take pictures of all failed structures, do a 3D solid model of them as soon as you understand how to do it, and then bring them to class. Let us be discussing them, and let us now use our design knowledge to now be doing failure analysis on them. If you start that, you are behaving like an engineer from day one. But don't forget, you need equipment. You need your measurement equipment, especially all I've showed you now are just for measuring length. I will show you other equipment that you need to have personally later on. So you don't tell me the thing is not in the lab. I don't care whether it's in the lab or not. Go buy your own. And nobody to listen to you. If you go out and you are failing, nobody, and you say, hey, the reason why I'm failing is that they didn't teach us this in the university. You say, oh yeah. And then you took their certificate and you are carrying it about. So that's it. So this is failure analysis. Let us go on. Now, this particular one is near the MetaMath office. If you look at this one, the date of its manufacture is written on it. These were built 60 years ago
We can't
the
see
year
the
of
screen
Nigeria's.
yet, sir.
Oh. Okay. I will have to slow down. Why is this happening today? The thing is just so slow. Everything slow. So when you can see, let me know.
We can see it, sir.
Okay. So I have to be waiting for some 1 minute before I refer to the new topics. Okay, so you see this drawing here. This picture is a concrete bench that was made 60 years ago. In fact, it was made 61 years ago, 1960, in the year of Nigeria's independence from the British. They lasted 50 years before any significant failure. They are located between systems engineering and metallurgy and materials engineering build offices. Observe the slender nature of the slab. They are slender, more slender than compare the slab here to the one you saw before. These are slender and they are modular. You can pack them into 1, 2, 3, 4 pieces, and so you can transport them easily. These were properly designed. This was when the British were still here. So the people who made these ones were engineers. They just forgot their engineers. They just called artisans and say, okay, so here you can see this one that was made by the British. Go and do something like that. And the craftsman said, yes, sir. And the craftsman did what he thought he saw. But the people who did the original thing actually thought they needed an engineering analysis before they did that design. So that this is the trajectory of Nigeria. We do what? We win failure, we win defeat, we snatch defeat from the jaws of victory. So if you see something that has been done well 60 years ago, and you now do that 10 years ago or 5 years ago, and you are doing something worse because you are saving money, you are giving it to the lowest bidder, you are doing it as quick as possible, you are giving it to your brother, so your aeroplane will be falling out of the air because you think all you need to do is to award. When you have a contract to award, all you need to award it to is just find somebody from your village, give him that contract. That's all you need to do. And then the plane falls out of the air, kills people. That's okay, if that's how you want to run your life. So you can see that it is not a matter of bigness. These are bigger, but they are failing. It's not. This one is a single unit instead of modular shape, and it is failing. In fact, see all the iron rods inside it, and it is just useless. This one is over-designed, 3 legs instead of 2. And the leg, even it was the leg that first of all fell out of it. Okay, let me wait now to see, wait a little bit because I've changed the page. I'm on page 19. Admin, can you see page 19 yet?
Stop sharing your screen just now.
What is it?
You stopped sharing your screen just now.
Did I?
Yes, sir.
No.
No.
Uh-oh. I didn't stop. I'm trying to share again. Am I successful yet?
It's almost on. It's on, sir. We can see it now.
The thank you, Emmanuel Oni, has been very, 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 very good. Josiah Adisola, thanks for your comments. Please, I want more people. Just go to the chat room, and if there's any problem, just send a chat. A single sentence or something like that can be very useful. So instead of me talking into the air and thinking I'm talking to people. So, okay, so you see how slender the slabs here are, and you see how modular it is. And I will show you. I will show you the 3D solid model I made out of this. And those are the kinds of things I want you to begin to aspire to do. And once you start doing them, then we now find out to analyze them, because the software you are using can actually do the analysis, simulation, amenities, even before you reach those places in your theory courses in class. So those are the kind of things you will see. So the question that will come, there are failure analysis posters. I'm on page 20 now. So if you have not seen page 20, please complain. I'm on page 20, failure analysis posters. What led to the failures we have snatched from the mouth of victory? What led to these failures? We already had working concrete benches before the others were constructed. Don't forget, the ones that are working, that have lasted for 61 years, were already there before contracts were awarded to make those cheaper ones that are bogus and useless. Why? Why did we get terrible benches? What really was the problem? What really is the problem? Is it design? Was it badly designed? Was it badly constructed? Did it fail during transportation? Was it a problem of supervision? Was it a problem of corruption? Were there bribery and corruption issues? What really caused this thing? Those are pertinent questions for us to ask. But I don't want us to answer those questions using conspiracy theories. Let us be like an investigative journalist. But now we are engineers. We use the tools of engineering to do our investigation by studying some of these things. So what I'm challenging you in our course on graphics is that you are going to draw your environment, just like environmental design students do. You are going to look at things that worked, things that failed, and you are going to analyze, if they worked, you are going to analyze why did they work. It could be light towers, it could be MTN towers, it could be anything. It could be gates in a place that has fallen down. Then you want to see, okay, were the supports not properly designed? Was it proper? Was it bad products that were all those kind of questions? And then you will now go and see whether we can redesign the support and get a better result. Those are when you are doing that, you are doing failure analysis, and that is some of the things that an engineer will do. So I'm going to page 21 now. So if I don't see any, comment that I am, if I don't see any, I'm not sharing. What is the problem? I didn't stop.
You can see your screen now, sir.
Frustrating. What page can you see?
21.
Okay, I'm on page 21. Good. I'm on page 21. Okay, so engineers talk quantitatively. So mark that. Engineers, if you want to talk as an engineer, you talk quantitatively. You will not say the beam is too small. You will say the beam should have been 3 inches thick, but it was 2.5 inches thick. That is different from, oh, it should be thicker. No, that's qualitative. It was 2.5 inches thick, it should be 3 inches thick. Or if you want to speak in SI units, you can say it is 1.5 centimeters thick, but it should have been, or maybe, maybe it was 3 centimeters or whatever, or 6 centimeters thick, but it should be 10. That is quantitative. Engineers talk quantitatively. So the whole of your training as an engineer is to enable you to react to your environment quantitatively, not qualitatively. You are not just opening your mouth and whatever comes out of it, just talking it. Observation. Everyone has an opinion on the failures. Most of the opinions have no quantitative basis. They have no scientific basis. They have no engineering basis. Unfortunately, those opinions could decide the next course of action. If the person who is taking the decision, if you are influential and you take and he listens to you, so this will, if the influence decision, then they will lead to another failure. They will lead to one failure succeeding another. That is why you had bad benches in engineering. Then when they are doing benches on the lagoon shore, you have bad benches. And when we are doing it in DLI, we even have benches that are worse than both of them. Whereas 4 iterations back, we had good benches. So because people who talk qualitatively, who don't know what they are talking about, continue to influence the decisions that we are taking. And if I tell you that some of the people who took the decisions are actually engineers, you won't believe it. But that's what happened. So one failure can succeed another. Whether you have your certificate or you are an engineer, somebody, doesn't mean you will not take bad decisions. What will decide whether you take good decision or bad decision is whether you are thinking quantitatively and practicing engineering in a quantitative way. If you don't, you are going to be taking as bad decisions as the society is taking. So this is what led to one failure succeeding another. In most of the failures, the slabs were okay. The failure were at the supports. Is it possible to quantitatively analyze these failures and come to superior actionable solutions? Is it possible to improve the concrete benches that were made 60 years ago and get better benches in 2021? I wrote this note 2020, you can see. But is it possible to improve on it and get better benches instead of getting worse benches? That is just for benches. That's just my own observation in my environment. What do you have in your environment that's of interest to you? Let us design those things by using quantitative modeling. Now, I am on page 22. So let me know when you people can see it.
It's on,
because
sir.
I'm now afraid. It's on. Okay. Now, quantitative answers, simulation and analysis. Quantitative answers begin with an accurate 3D solid modeling of a properly designed component based on concrete bench consisting of 2 arms, 2 supports, a slab, and a backrest. Each of these is designed with proper reinforcement and tested with static loads. Scenario analysis is coupled with simulation to first examine existing design, seek its improvement until optimality. All of these things begin with a solid model here. So you can see why I'm saying that engineering graphics, solid modeling, 3D solid modeling is the most important course you are going to take, because everything you are going to do is going to be based on accurate solid model. And you will see how we do it shortly. I'm going to show you examples in today's lecture. I will show you some examples. So I want to whet your appetite. I want to challenge you. I want to mop up all the time you waste. I live near a hostel, and the amount of noise you make shows me you are so idle. You are either idle because you don't know that there is a way that you can use your youth to learn skills that are going to make you very wealthy and make you influential in your society. You think all you need to do is to be enlarging your tongue or your throat and your lungs and be shouting across the window to the people of opposite sex in the other hostel and be disturbing the whole of the neighborhood. I'm not going to repeat some of the things you say, but I'm just trying to mop up some of the free time you have, shouting. So let us try and gain skills here. There are so many things for you to learn that even if it is solid modeling, you are doing alone here, it can take the entire time and you will be increasing your skills and you'll be able to do a lot for yourself. You could even take certification courses in Fusion 360 and some of the other software that I'm going to introduce you to. So all those things you could do as undergraduates. So there is enough to do. If you finish your degree in Unilag and you are jobless, it is your fault. It is your fault. It is not because we don't have this, we don't have that. It is because you just wasted your time. You were busy shouting. You spent all your time shouting and enjoying yourself, not knowing that you could have been learning skills. So everything we are going to do, we begin with solid model. So you start with accurate 3D solid model of a properly designed component-based concrete bench consisting of 2 arms, 2 supports, a slab, and a backrest. Each of these is designed with proper reinforcement and tested, virtually tested with static loads. Then we do scenario analysis coupled with simulation to first examine existing design, seek its improvement until optimality. This begins with the solid model here. See it. So this is my drawing now. This is my own drawing. By going to page, let me just go back now. I go to, can you see page 19? Is page 19 showing?
No, sir.
Not yet, okay. Let me know whether when page 19 is showing.
You can see it, sir.
Okay, so I went with my tape, with my measuring equipment, and took the dimensions of page 19. This drawing here, I took the dimensions, and I came back to my computer, and when I spent time on it, this is what I got. I just drew by taking the dimensions of the drawings you saw there. And I'm now on page 23. So if you can see page 23, that is the three-dimensional solid model of what you saw on page 19. Can you see page 23 now?
Yes, I can see it.
Okay, if you can see page 23. So this is what I got. Now, I went with my tape. I wasn't expecting the Department of System Engineering to provide me tape. I went with my own tape and I took the dimensions and I came back home and I did this drawing. So I did the drawing in several ways. For instance, this, what you have on the right-hand side is the same drawing. I just increased the transparency. I just put a transparency on the different things so that you can see the reinforcements that are inside. So you can see this reinforcement inside. So you can see the reinforcement. I've not done any analysis yet. I've only done 3D solid modeling. This is what is within the scope of the course we are taking right now. Just do your 3D solid model of your environment. 3D solid model. We can go on, we can do sectioning, we can do orthographic projections, we can do so many things of it, but we are going to just go straight and show you how to do the 3D solid model. So once you can do the 3D solid model, then you can now decide to show it in several ways. You can show it where normal way, where you just see the concrete. Here, you don't see the concrete, but the concrete is made transparent so that you can see the reinforcement rods that are inside. And then the next stage is to now put this through a simulator where we put maybe 3 people sitting on this, put their weights on it, and now see how those weights will be resisted by the support, by the benches, the backrest, as well as the support, and see how close to the factor of safety that we are doing using static loads. Then later on, we can try dynamic loads. Then we can now be sure how far we are from failure, and then we apply a particular factor of safety. These are not things that your artisan will be able to do. So if you just tell an artisan to come and look at that thing and do, of course, he will do what his education has given him to do. And if you think that what university is supposed to do for you is to make you an artisan, then you are in the wrong place, because we are not going to make you an artisan. We are designed here to give you enough science that you can apply to technology to make products. That is what we are supposed to do. It is for you to now be very active on your environment and be asking questions and be doing your models and have a portfolio of models. Every year you spend in the university, have 50 to 100 models that you have already done and that you are thinking about. And if you begin to think like that, but as you are taking more and more courses, you'll be getting more and more theories to use to analyze those models, and then you'll be designing. Then you'll be an engineer. If you wait until you just cram and pour the result to the teacher and you go on, well, you will learn enough science, but you will not be an engineer, and you are going to be laughed at for the rest of your life. And then you may be hungry in addition. So that is, if that's what you want, it's up to you. So this is a solid model of a design concrete bench. 3D solid model of the concrete bench with the second picture emphasizing the internal steel reinforcements. We have prepared this for simulation optimization for failure analysis and design. The reinforcements are exposed by the opacity control feature of Vision 360. We will talk about that when we get there. I'm on page 24 now. Can you see page 24 yet?
Yes, sir.
Okay. Now, purpose of the rest of this lecture, I'm going to give you a guide and a description of the software suite for this course. You will learn where they are located and different ways to get your copy and install on your system. We are going to use 3 principal software for this course, and I expect everybody, if you do not install the software, don't come to the next class, because it's going to be hands-on, and I'm going to expect you to be there. I'm not going to wait for you. If you want to cheat yourself, if you do not install the software by next lecture, you are wasting your time. So all the software, there is no software there that is not free. Everything is free, but you have to identify yourself as a student to get the free Vision 360. Vision 360 is about $400 per year. But for a student of University of Lagos, it is completely free. But you can go and get that directly on the Autodesk website. I will give you the address if you don't already have it. Integration and preparation for lectures, things to do before and after each lecture. minimum hardware requirements to install the software will be told you. And then, so this is what we are trying to do now. We're trying to get to some of those things right now. So here on page 25, I hope you can still see my page 25.
Not yet, sir.
Okay.
You can see it now, sir.
People have seen it.
No, sir.
Oh, sorry. Okay. And no, I made a mistake. Sure, you can still see it, page 25.
Yes, you can see.
Okay. So this is the Fusion 360 is the design environment we will use for this course. This course will teach you Fusion 360 as a way to do 3D solid modeling. And later on, in later courses, we will teach you how to use the same Fusion 360 to simulate and animate. And later on, we might add another component like computational fluid dynamics to add to your panoply of software to be able to do more simulation when you are doing multi-physical problems, when wind and fluids are interacting with solid interfaces. But right now, we are just going to ask you to install Fusion 360. We shall know and apply enough Fusion 360 to learn to use its GUI. GUI means graphical user interface, and API means application programmers interface, to create graphical objects and learn Python in the process. If you don't know how to program Python, don't worry. I will teach you the little amount of Python we will need to just whet your appetite. After I've given you sufficient Python, I will expect you to go and learn more Python on your own, because the syllabus does not envisage we will teach Python, so we don't have enough time to do it. But I will give you enough, and it is a very good thing for you to learn. That's another skill. You learn your skill in 3D solid modeling, you learn how to program Python. Those two things will fetch you your daily bread. If you cannot know Python and know solid modeling and know how to simulate and be hungry. It is not possible. So if you are hungry because you have no skills, it's not because there are no jobs, because you are not qualified to take the jobs that exist, because these jobs are coming at rates faster than we can fill them. Even in cattle colony in Nigeria. If you already know Python or Fusion 360, you are at an advantage. If not, it is an exciting opportunity to learn as we move along. We will show you how to do several things. But if you know and you are moving ahead of the class, that's better. On pages 26 and 27, you have the system requirements. I'm not going to pause there because you can read those system requirements on your own. You can read those system requirements. There are 3 software that we're expecting you to install. Fusion 360 has the highest spec. That's the first one. The second thing is Python interpreter. I will show you where to get that. And then the third thing is Visual Studio Code, which is our preferred integrated development environment. There are other integrated development environments, but I am insisting for this course only, just use Visual Studio Code. You will see later that insistence is not trivial, because there are things that even better integrated environments like PyCharm will not be good enough for us, because there are some things we want to do that PyCharm cannot do. So if you, I'm on page 28 now. I'm on page 28. And I'm saying here that Python is perhaps the most popular beginner's language in the market today. It combines the best practices in object-oriented programming in a rich function-driven environment. The results are as follows. You can create simple scripts and applications without needing to get too deeply into the object model. The object model is still there all along, and you can create advanced applications that are fully object-oriented. All those things may look like jargon to you. They will be getting clearer as we move on. It has a huge array of libraries for most scientific, graphical, and artificial intelligence applications. If you do these things outside Python, you are probably working harder than you need to. So I'm moving now to page 29. To properly install, okay, no, I think page 29 is superfluous. I'm moving to page 30 instead. I'm now talking about Visual Studio Code. Visual Studio Code is the integrated development environment that you will need. There are many ways to interact with the Python language. There are many teaching things online. They tell you to use the command line. Nonsense. You are wasting time. Command line is just a waste of time, or REPL or IDLE. Go and get a proper IDE. They are free. I don't know why those Oludramatas are still teaching the REPL command line and all those things. I don't see any good you doing things in the hard way. It's just like somebody giving you a lawnmower and say, okay, it's good for you to still use your cutlass to cut the grass so that your hand can peel, so that you can know how to use the lawnmower. I don't buy that. The integrated development environments are the ways I want you to interact with Python. The figure below is certainly not exhaustive. There are many of the IDEs should provide excellent fully integrated development systems to write, debug, and run your code. We will focus on only one. The one we will focus on is called Visual Studio Code. Visual Studio Code is an integrated development environment. It is only here that you can integrate not only the coding, debugging, and execution of your code, but Fusion 360 API environment as well. So if you use your Python with Visual Studio Code, you can integrate Python and you can integrate Python and Fusion 360 at the same time. So you can work in the same environment, because the Fusion 360 can create Python code for you, which you can improve and do some things with. So that is the way I want to teach. So if you are, some of you might have used Python already. I'm sure some of you might be familiar with an integrated environment called PyCharm. There's another one, the IDLE extension. There is Visual Studio. There is Spider. There is Eclipse. There is Atom Freeware. There is PyDev Eclipse. There is Wing IDE, Tony MIT license, Eric. There are many of them. But we are going to use Visual Studio Code only, and nothing but Visual Studio Code. So just know, for this course. After this course, go and do what you like. But when you are in the course, use Visual Studio Code. It will become obvious to you as we move on why I am that insistent. If you use any other thing, you are going to waste a lot of your time and you won't get results for this course. So there is an integration between Visual Studio Code and the Fusion 360 API environment, which allows you to use Python in the Fusion 360. That is the reason why I'm insisting on Visual Studio Code. I am moving from page 30 now. So to get Python, you go to python.org. So if you go to python.org, you can download it. Okay, yes, okay. You'll get there, but there's no graphics there. So you get to python.org, and when you get to python.org, it may no longer be true that is the version 3.76 that you will use. In fact, it seems as if Fusion 360 has improved. It is just that no matter what Python environment you install, it will work. Before, it was only working with version 3.7.6. So I think you can go ahead and install any version you like. If you have any problem, I am sure that 3.7.6 will work. But install any time you go to the python.org, it will allow you to install any version you like. And last time I installed, it was version 3.8.5, but that last year. So they may have newer versions now. But what I am sure of is version 3.7.6 will work with Fusion 360. Can you see page 31 now?
Yes, sir, you can see 31.
So you can see page. Okay, good. So if you can see page 31, that's it. You may install the latest if you want Visual Studio Code IDE. So you can do so three software: Python, Visual Studio Code, and Fusion 360. I have the links are on this slide. So once you download the slides, you will be able to see what links you need. So you can contact Mr. Oriola in my office. He will give you, he will give you access to the video and the audio of all we have been talking about today. You will hear, you will see what we have been talking about, and then all the links you will see. So install those 3 pieces of software. Some of you, if you are interested, you might install Anaconda if you want. Anaconda makes things easier, but I don't want to. You don't have to if you don't want to install Anaconda. Anaconda is also free. All the software for this course, everything is free. So it's free for you. Everything is free for students. Some are free for all, but Fusion 360 is especially free for students. But if you are not a student, so the only time you can use Fusion 360 for free is now until you finish your youth corps. After youth corps, when you begin to work as an engineer, they think they've helped you enough, and then you should pay them for the development effort. And I don't think it's unfair. By that time, if you have done the right thing, you should be making money at that time. And there's no reason why you should not be able to pay for a software that is that fantastic. The software is really good, and their business model is fantastic. So those are things that we can talk about later on. This is on page 32. You have the link for Visual Studio Code, and then you have more information as to how to install. On page 34, you have more information about Fusion 360 and how to launch it. I'm not going to talk more about these things. I'm just going to move all the way to page 37. I will wait a little bit until you reach page 37. On page 37, I now go inside Fusion 360 to begin to teach about Fusion 360 inside it. And I think it's not a bad idea to pause this lecture here today. We still have about 3 minutes or 4 before the time is up. But I think it's a good idea to leave it here. As I told you before, I won't talk again. But if you have questions or you have anything, let me know. So if you have any issue, let me know. You can go to the chat room, and once you are given the permit to go to our website, you can download both the slides as well as the video and can listen to it at your own convenience. So if there are questions, we can take 1 or 2 questions verbally. If you raise your hand digitally, you might be allowed to unmute your mic and talk and ask questions because we have 3 or 4 minutes to go. If you have anything, if you have any other thing, you can go to the chat room and tell us. Of course, somebody is asking whether you can use Fusion 360 to test the strength of material. Of course, you can. You can. Sir, is the exam theory or practical? It will be both. You will have practicals, and then you have theory. You have both. You have both, but you don't need to worry. My exams are designed to make sure that you fail if you don't understand the practical. So I will always set it in such a way that you can't pass unless you can do something with it. So you don't need to cram anything. If you just obey the simple instructions, the exam will come to ask specific questions, and people who have not tried those things will fail the exam for sure. I will be very sad if you pass without knowing how to do your 3D solid modeling. It will make me very sad. I want everybody who doesn't understand it to fail, and I want everybody who understands it to get A. So I don't want anything in between. There's no reason why the entire class cannot get A in this course. But when you get an A, you will know why you got the A. You will know you worked for it. And when you fail, you will know that's what you deserve. So you will know you worked for it. So anything, you are going to get what you deserve. I hope. I don't like people to not get what they deserve. Well, I am not admin. Is there anybody raising the hand to talk that needs to be unmuted?
No, sir.
Okay. So if everybody wants to go, it's just a minute to 4 by my clock here. I want to say thank you for your attention, and I hope we will meet again next week at the same time. We will arrange a time for tutorial, but at least let us make sure you install all the software and download what you need to download. From tomorrow at the latest, you can visit the website that you'll be given, and you can download the slides, you can download the video and audio together. So, and then you will also get a place where you can go and ask questions. And so you can ask your questions offline. So even if you didn't ask questions during in the chat, you can put those questions directly. And if I have the time, I might have answered you before the next class. So there are several ways to interact. So if you don't interact, it's your fault because I'm available. And for now, goodbye. Have a nice day. Thank you for your attention.